Good morning, everyone. Today we're going to take the normal distribution, which we worked with last week, and basically standardize it. Up to this point, we know that a normal distribution has a very specific mathematical function, that if we would graph it, we would see our standard kind of bell curve or standard curve. And from that, you can find probabilities within ranges, which basically correspond to the area under the curve, or you can find the cutoffs of the numbers with a certain given area. And you can do that by understanding some of the relationship between the mean and the standard deviations, or probably more likely you would use your calculator with the norm CDF and the inverse norm and applying the correct syntax and find these different cut numbers or probabilities. But today, as I said, we're going to be looking at the standard distribution, so let's get into that. Standard distribution is sometimes known as the Z distribution, mainly because we tend to use the letter Z instead of X to be our random variable. You may have had situations where you have different scores, whether it's a standardized test, and you're given Z scores. And so after today, we'll take a closer look as to what those mean. But basically, a Z distribution or a standard distribution is taking a normal distribution and calculating Z by taking the value of your normal discrete variable, or not discrete, continuous random variable, subtracting mu and dividing by sigma. What this all means, basically, is you take whatever that normal distribution function could be, and you move it, and you shift it a little bit, so that the mean now is 0, so it's centered at the y-axis, and the standard deviation is 1. So whatever the data is, you basically turn it in to this type of curve. And again, we would still have these inflection points being at 1 standard deviation. Okay, but in this case, it's basically just going to be 1 and -1. Okay, so that same percentage would always occur. Now, the formula that will come from this, or lead to this, I should say, is going to be 1 over radical 2 pi. We still have e, but here it becomes -1/2 z squared. If you compare that to what we looked at next week, you would see that with this substitution, this would kind of develop. And that is going to be now for z from infinity to -infinity. So as a function, this is what it looks like. Again, we tend not to graph that function because the calculator is all set up to answer questions involving these. Now, if we do use the calculator, we can basically just replace our normal mean that we would have had last week and standard deviation with 0 and 1. It even turns out that if you omit those, this is, most calculators, going to be the default. But let's see how this can play out and how we can work with these types of problems. One is that because we're taking maybe different sets of data and want to compare them in some way, we can standardize it. And here's a nice simple situation. We have Kelly taking 2 different courses, history and math, and on a certain test or an exam or whatever you might call it, she had 73% in history, 66% in math. Well, which one did she do better at? Well, that's debatable. Raw score, of course, she did better at history. But relative to her classmates, which one did she? Well, in history, the mean was 68. Here, it was 62. So she's above in both of them. But here's the standard deviations. So what we can do is use the z-score for each of these to get a better comparison. So in history, for example, her z-score is simply going to be her 73, which is the x, minus the mean, divided by the standard deviation. And what this comes out to be is approximately 4 or 0.48, I believe. 0.49. Where in math, it's the mean, the score, minus the mean over the standard deviation. And that turns out to be 0.588. So these are the two z-scores. So in other words, this basically means that she is 0.49 on the positive side of the mean in terms of the standard deviation. So the score relative to all of the scores would be about here, 0.49. So that's where she scored. Whereas, of course, in math, she'd be about 0.588. So she'd be on the other side of half that standard deviation. So relative to her peers, she did better in math than she did in history. And we all know that even though we like to think that students all meet certain standards, when we have comparison tests or norm reference tests, this is how it's done. You're compared to the people that are also taking the test or also performing some situation rather than how you did individually. So this is one way to use the standard distribution. Another is kind of a historic, I guess, look. Because in other words, what if we didn't have a calculator? Well, if we didn't have a calculator and we tried to answer this question, let's say we want to find k, such that the probability that x is less than or equal to k is 0.95. And remember, we always have to be told something about this distribution. Let's say it's normal with mean 70, 10 squared. Of course, that's just going to be sigma. Now, the calculator would allow us to very quickly do this. We could say k would be the inverse norm. And then if we use the proper syntax, 0.95, 70, 10. Now remember, if this happened to be greater than, we would have to change this. We're just kind of taking the supplementary or complementary area, the rest of it to add to 1. But as an historic appreciation, if we weren't able to do something like this, what we might want to do is change it to a standard distribution. The reason being is on page 824 of your text, there is a table. This is how many of these things used to have to be done, where someone already did all the calculations using these functions. So no matter what type of a situation you had with a mean and standard deviation, you standardize it so everyone could use the same table and they're still going to answer the question. So what we could do here is change it to basically say we're finding the probability that z is less than or equal to k minus 70 over 10. And we're saying that's going to be 0.95. Well, all of this, or this, can be found from the table. And from the table, it's 1.645. So we're basically saying that this number has to be equal to 1.645. These are all approximations. So we end up finding k to be about 86.5. So the table is important if you didn't have a calculator. So a little bit of a historical perspective. Quite honestly, that's not going to be used a lot, but you might find yourself in some courses where you do have to make use of some statistics tables. But typically, the best thing about a standard distribution or a z-score is that you compare maybe data from different situations, but you still want to make some type of a comparison. So that's what we have for standard distribution or z-distribution. Work on the problem set from 29C. In a couple days, we'll take a look at just a random variety of problems involving all sorts of statistics and probability. And by the end of the week, you'll be given some type of a handout, a worksheet, and work on that through the Easter weekend. And next week, we'll be able to wrap up everything involving statistics. Again, thank you for your patience, and hopefully these videos are helping. Continue to stay in touch if you have any questions, and have a nice day.